So as a brief introduction, my name is Allan Jude. I'm the VP of Engineering here at Klara. I'm also a FreeBSD and OpenZFS developer, and I've been working with ZFS for quite a few years now and been a developer for about 5 years. And we're going to talk about what's new in 2.0 and how that might impact your existing installations and your planning for new installations. So to recap what we're going to talk about, we'll start with a quick intro about how OpenZFS 2.0 came to be. Then we'll talk about what some of the new features are, and then how those will impact your existing installations, but also how you can get access to those features early if most operating systems aren't shipping 2.0 yet, but that doesn't have to stop you. And then how you will plan to take advantage of these features in future installations you might do. So to start, where did OpenZFS 2.0 come from? So after a large multi-year effort by both the ZFS on Linux and FreeBSD communities, we've managed to realize the dream of the original OpenZFS project. Back in 2013, when the OpenZFS project was spawned after Oracle shut down development of OpenSolaris, the idea was to have one source code repository that contained all the ZFS code, and then each operating system would then pull the code from that, add whatever glue and other bits they needed to make it work on their operating system, and use that to have their version of ZFS. The prerequisite for that to really work, though, was having some way to test that common code so that we could make sure it was right without needing the OS-specific glue. And it turned out over the course of years of trying that it wasn't really commercially viable to for someone to maintain this repo that contained only the common code, because ZFS isn't really usable as just the ZFS code. It needs to integrate into an operating system. So for a long time, that was basically, there was the OpenZFS repo on GitHub, which was a fork of Illumos, which is the open source continuation of OpenSolaris. And people could contribute or propose changes to that, and some of the ZFS maintainers would take care of the effort of getting that integrated into Illumos, but it was quite slow. But that's where both the ZFS on Linux and FreeBSD projects got their ZFS source code from. But it also had this problem of, something that got fixed on Linux didn't necessarily get contributed back up to Illumos to eventually get pulled down into FreeBSD, or even if it did, it could take a year to make that trip. And that wasn't very conducive to what we wanted. So after a bunch of talking and a bunch of sorting it out, we took the ZFS on Linux repo, which had the most new features, and separated the Linux-specific bits out onto the side, and also added the FreeBSD-specific bits into it. So now we have one repository where all the common ZFS code is in one place, and it also includes an OS directory with the required glue code for both Linux and FreeBSD. And over time, we expect to add OS 10 and maybe Illumos as well. With those in place, it will allow it allows not just the development to be combined and all of the operating systems to get the features more quickly, but it means that the same code can be tested on both operating systems at the same time. And so when someone proposes a patch to OpenZFS, it can actually be tested automatically on Linux and FreeBSD on GitHub, is the way it exists today. So once we reached that milestone where we had one set of code that worked very well on both Linux and FreeBSD, that was tagged as OpenZFS 2.0. And that's what we're going to talk about today. So starting off with what's new, these are basically the big headline features, although there are hundreds of smaller changes and fixes that have happened as well. So the big one is sequential resilver, which we'll get into more in a minute. Slightly confusingly, there was a previous feature called sequential resilver, but it wasn't as sequential and works quite a bit differently. And so we'll talk about that. So that's resulted in a bit of a naming change. the existing resilver code that's based on the same concept as a scrub is now called a healing resilver, and this sequential resilver is different, but we'll get into that in a minute. Another big feature that was added is the persistent L2 arc. Again, we'll expand on that on a later slide, but previously, any content that got saved into the L2 arc was lost on a reboot. Basically, when you rebooted, we treated the L2 arc as empty again and started filling it up. With this feature, anything that was cached in the L2 arc will be reloaded, and you will basically be able to start with a warm cache after a reboot, which can make a big difference, with how bad performance is after a reboot, depending on what your working set is like. Another big feature was the introduction of Zstandard compression, which was one of my projects. This provides a new high-performance compression algorithm. While not quite as fast as LZ4 usually, it provides much better compression, including better than gzip, while being much faster. And again, I'll expand on each of these points later. There's also a redacted replication feature, which allows you to replicate sensitive data, to replicate your ZFS datasets while excluding specific sensitive data. For example, this was designed to be able to back up databases that might contain things like credit cards or social security numbers. It allows you to replicate the database while redacting out the very sensitive data. This can also be used for standing up development environments. If you need to clone your e-commerce database or whatever, you can copy all the data and just zero out all the credit card numbers so that the dev environment doesn't contain anything sensitive while still having all of the other data that you would have to have an environment typical of your production environment. And then lastly, the one that I was really grateful for is the ZFS manual pages have been reorganized. So rather than one giant manual page for ZFS and one for Zpool, each subcommand has its own man page now, so they're much more readable and cross-referenced. So one of the biggest features in OpenZFS 2.0 is the new resilver code. But to understand it, first, we're going to have to look at what the old resilver code did. So starting at the beginning, what is resilvering anyway? It is the term for rebuilding a RAID array after a disk has failed. The kind of etymology of this is in ye olden days, the mirror like you have in a bathroom was made of glass with a silver backing that provided the reflection. But the silver would oxidize over time and lose its reflectivity. And so you had this thing that people would do called resilvering a mirror, where they would replace the silver with fresh that wasn't oxidized, and then the mirror would be good again. And so when you had mirrored disks and one of them failed and you replaced it, you would resilver the mirror so that it was good again. So a normal hardware RAID array, like done with a controller card, does this by sequentially rebuilding the whole array. So if you have a mirror or even a RAID 5 of many disks, when one fails, it just starts at the beginning and goes through every block and figures out what needs to be rebuilt. This is high performance, but not necessarily fast, right? If you have a RAID array made up of a bunch of 10 terabyte hard drives, but you only have 1 terabyte of data on it, you're going to, if it's 5 drives in a RAID 5, you would have to go through 40 terabytes of data in order to finish the resilver. Whereas ZFS was optimizing this. It would be able to look at its data and know which parts of the drive actually had data on them and which didn't. And so it would only have to resilver that 1 terabyte instead of all 40 terabytes. So this oftentimes would be faster. But as it turns out, not always. So a normal healing resilver, which is basically just a scrub, except for, every block on this hard drive is blank, so we're going to have to repair them all. So in a normal healing resilver, ZFS would walk through the tree of blocks that it's made up of, right? So it would start with this uber block at the top, of which there's one, and then that points to a bunch of blocks that describe your data sets, and then in each data set you'll have these indirect blocks that basically contain an array of either other indirect blocks or data blocks. And so it would have to walk through this whole tree, and the main problem with this is that these different types of blocks are usually written to different places on the hard drive. And with spinning drives, seeking to these different places is a lot slower. And so with a healing resilver, rather than starting at the beginning of the drive and reading every block in order, you're skipping around and reading these indirect blocks to find some data blocks, and then reading them, doing the resilver, and then moving on to the next one. And so you can see if we did that, you start at the Uber block and you go down to the indirect block, and then you read the first indirect block in each of its data blocks, and then the next indirect block in each of its data blocks, and keep moving on and on like that until you've read all the blocks. So you're going to read some of this data sequentially, but not very fast, because you're going to keep skipping around to these different bits of metadata to find out where the next block is. And because of the way copy on write works, if you've modified some blocks, they're going to be very out of order on the disk. So back in 2017, Saso Kiselkov and some developers from, I think, Nexenta introduced a feature which at the time was called a sequential resilver, although now we just call that a healing resilver. And instead of doing it in this order, what it would do is it would start at the Uber block and it would do a scan phase where it would read these indirect blocks. But when it found a data block, instead of reading it, checking the checksum, and possibly needing to write it to the replacement disk, it would just add it to a list when it ran into a data block. So it would scan all the metadata, but when it found actual data that needed to be updated, it would just put it on a list. And it would keep scanning like this until that list was full. Then it would take the largest contiguous chunk in that list and actually issue it and actually do that bit of resilvering. Then it would go back to scanning until the list was full again. And by doing this, instead of doing it in the order of the objects in ZFS's hierarchy, it would try to find big contiguous chunks to do, and that would make it quite a bit faster, sometimes as much as 15 times faster than the previous to 2017 version of resilver. But it still wasn't truly sequential. We were just batching to try to improve things. So if previous to OpenZFS 2.0, you did a zpool status while a scrub is going on, you might see those two different progress parts, the scan and the issue. So scan will go through and find blocks, and then once the list is full, it will issue some of it and then go back to scanning. And eventually, once it's all issued, your scrub is complete, or resilver is complete. So I just wanted to take a moment to mention that here at Klara, we do OpenZFS support contracts. So if you sign up before the 28th of February, then for a ZFS support subscription, then we will include a complimentary infrastructure audit. So if you want us to look over your ZFS configuration and make sure that everything is configured correctly and that all the tuning is right and that you're doing everything to protect your data, we'll include that for free if you sign up for a subscription before the 28th of February. If you head over to klarasystems.com/support, you can read more about it or get signed up, or you can just email us directly, team@klarasystems.com. So the new sequential resilver, or sequential rebuild as it was called originally. This is a feature that was developed as part of DRAID, which is a new feature in ZFS that'll be coming in OpenZFS 2.1. We'll have to spend a whole nother day talking about that some other time. So rather than walking that tree of blocks like the healing resilver does, this one just uses the space map, the ZFS data structure that keeps track of which data or which blocks on disks are used and which ones are still free. So it just looks at the ranges of blocks on the disk that are allocated. So it maintains the advantage of a ZFS resilver of not having to do every single block like a hardware RAID card does, but it just looks at which blocks are allocated and which aren't, and it sequentially walks through the disk and does the resilver. But there are some limitations. The first main limitation is this presupposes it knows the layout of the data on the disk. So for mirrors, that's fine, right? Because in a mirror, every disk is laid out exactly the same. So you read a good copy and write it to the other mirrors, other members of the mirror. Or with DRAID, where the permutations of how the data are stored are pre-calculated. But it doesn't work with RAID-Z. Because of the way RAID-Z works, the space map just knows that within the RAID-Z itself, it is this block. But it doesn't know enough about how those blocks are laid out on the RAID-Z to know how to rebuild it and what other data it would need to copy to be part of that same stripe. So the space map doesn't contain enough detail to allow it to rebuild a RAID-Z. But if you have a pool made up of mirrors, this new resilver can just use the space map and walk through the mirror and resilver it very, very quickly, as opposed to having to walk through all the metadata. So, in the simple case where you have a pool made up of, say, 5 sets of mirrors, so you have 5 pairs, when a disk fails, you replace it and it'll just go to the good half of the mirror, start reading from the beginning of the disk to the end, skipping any spots that are blank, and rewrite the data to the new mirror. So your resilver speed should be as fast as the disk can go, as opposed to a scrub-based resilver or healing resilver, where it's going to have to read metadata from all over the place in order to find out which blocks it needs to copy. So the advantage of this is that it's much faster. However, there's a downside. Because you're not walking through the indirect blocks, you don't actually know the checksum of each block. So in a normal healing resilver, as we're reading the data from the remaining copies, ZFS checks the checksum to make sure it's correct. And if it's not, it'll look for other copies, and failing that, we'll not be able to recover the data. But it can verify each block as it does it. This sequential resilver doesn't have access to those checksums, so it's just blindly copying the data. Now, in the case of a 2-deep mirror, which is the most common configuration, you have one disk remaining in the one failed disk that has been replaced. If there's only one place to copy from, the checksum doesn't matter so much, because you were either going to copy the data or decide it was corrupt and not be able to copy it. So it is considered acceptable to just copy it all and assume it's right. But it will actually trigger a normal scrub, basically a healing resilver, after. So while the sequential resilver itself isn't able to check the checksums, once the resilver is complete, it will trigger a scrub to go through and check all those checksums and make sure everything is right. So in the end, the sequential resilver takes longer because it has to do whatever it has to do and then do a full scrub anyway. But it gets you back to n+1 parity much more quickly. So, if in our example where we had 5 sets of mirrors, where one disk has failed, we put the replacement in, we do the sequential resilver, and get a second copy of all of the data off the remaining drive in that VDEV. Now, while we're doing the scrub, if the first disk were to fail, we at least still have a copy of every block. Whereas if we had done just the slower healing resilver, that might take, days instead of hours, then if the first disk failed, now we've lost both halves of the mirror and the data is gone. So this sequential resilver allows us to get back to relative safely very, very quickly, and then go through and verify all the checksums. So that's helps you get back to having an acceptable level of redundancy much more quickly, and then we can go back and double check that all the data is right. In the end, it doesn't change the outcome, because if the copy on the remaining half of the mirror was bad, then we don't have a working copy either way. No matter which type of resilver, even if we had done the slower resilver, if the copy on the remaining part of the mirror was bad, then there was no way to recover it anyway. And that's why RAID is not a backup. So moving on to the persistent L2ARC feature that we talked about. So the L2ARC itself, which is a special type of auxiliary VDEV, usually some type of flash storage, is basically contains just some data pointed to from the ARC. So the ARC, the adaptive replacement cache, is the buffer cache in ZFS, and it caches commonly used data. As it is getting full, it will start taking blocks in the near the end of the list that are about to be evicted, that will soon face eviction, and starts writing them out to the L2ARC devices. And then it replaces the copy of the data it has with just a small pointer saying, this data is now on this L2ARC device at this offset. And so when you go to read that data, you find it in the ARC, except for you don't find the copy of it. You just find a pointer saying, we don't have it in the really fast ARC, but we have it in the fast L2ARC, so you don't have to go read the slow disk. But this meant that after rebooted, that the ARC, which was in RAM, would be empty, and so wouldn't contain all these pointers, and so you'd have no way of knowing what data was where on the L2ARC. So we just treated it as empty and started filling it up again. With this new feature, we keep a linked list on the L2ARC device of enough information to rebuild those ARC pointers after a reboot. So as we start writing data out to the L2ARC, we build up a list of instructions of how to recreate those pointers and put them in this list. And then when you reboot, we can read that list and start recreating the pointers. And this is done asynchronously so that it doesn't make booting take any longer. It just means if you try to read the data before the L2ARC is reloaded, it will go to the slow disk because it doesn't think it has a copy. And to optimize things, instead of updating that linked list every time something gets copied out to the L2ARC, which is basically happening in the background constantly, it updates the linked list only after each gigabyte of data is written to the L2ARC. So it does it in big batches to make it more efficient. So that means, if you unexpectedly reboot, you might not have the ability to reload the last 1 gigabyte of data that was written to the L2ARC, but your L2ARC device is probably many, many gigabytes, and so you're only missing out on the very newest data. And again, it's just cache. It's not the only copy of the data. It's just a cache copy. And so as you boot up, it will walk through that linked list and repopulate the ARC. And in actuality, it's 2 interleaved linked lists because being able to read 2 of them at once was found to be quite a bit faster. Also have a small tip here. If you are using an L2ARC device, by default, the write limit, the speed at which the L2ARC is filled, is defaulted quite low. It's only 8 megabytes a second. This default was derived back when the biggest flash disk you could buy was 25 gigabytes and could only be written so many times before it wore out. Now, while SSDs still have wear out limits, they're usually in the terabytes now, or even petabytes. So it may make sense to increase that number to allow more data to be written out to the L2ARC so that it is more likely to contain data that you're actually going to use again. But you don't want to raise it too high because as you're if you're doing operations that read a lot of data, for example, a backup, you don't want to end up writing a lot of that data to the L2ARC because it's not going to stay in the cache very long. You're reading it once and then probably not going to read it again until you do another backup, which might be a week or a month away. So you don't want to raise the limit too high because then you'll just be needlessly wearing out the device. And if the SSD is busy writing all the time, it won't be fast at reading. So you do want to have a reasonable limit, but maybe 32 megabytes a second makes more sense depending on your L2ARC device and what its write endurance is and how long you expect to keep it for. Then we get to the fun one, because I worked on this, Zstandard compression. So this adds a new modern compression algorithm to ZFS. So this was written by Jan Collet, the same person who wrote the LZ4 compression that's most commonly used in ZFS. And his goal was to make something as good as gzip, so compressing as well as gzip, but faster by using modern programming methods. And some advancements in the compression space. So one of the first things about Zstandard is we actually have two different types of Zstandard, Zstandard and Zstandard fast. They're the same algorithm, but the fast mode disables a couple of the better compression parts to go even faster. And in normal Zstandard, like in the command line version, those are done as the negative levels. But anyway, just as gzip has the 9 levels to pick through, right? Gzip 1 through 9, Zstandard has 40 levels in the version I implemented in ZFS. So there's 1 through 19, as well as -1 down to -1,000 with, after -10, I only went in blocks of 10 or 100 instead of, adding thousands of levels. But this allows you to decide how much compression you want on a data. So you have a full range of choices between, Zstandard in the very fastest modes can be even faster than LZ4, or if you do Zstandard-19, it can be extremely slow as 5 megabytes per second per CPU core. But it offers compression that can be even better than gzip. So depending on your use case, you will be able to choose what speed of compression or how much CPU time you want to trade in order to get more compression. And so with the default level of Zstandard, which is level 3, compared to LZ4, an install of the operating system will usually get compressed about 3 to 1 instead of 2 to 1 with LZ4. So that gives you an idea of how much more compression you can expect, depending what it is. Now, if it's a database and you don't have an overly small record size, you can get as high as 5 or 10x compression. So it can make a very large difference, especially when combined with the compressed ARC feature, which allows you to have or to cache the compressed version of a block. So if you have a 128 kilobyte block that compresses down to 32K, then you can cache the 32K version in memory and just decompress it each time you need it and be able to fit a lot more in your cache. Because one of the advantages of Zstandard is that even if you compress at the slowest rate or the fastest rate, the decompression speed is always fast. So, if you use Zstandard-1 that compresses at, 500 megabytes per second, or Zstandard-19 that compresses at only 5 megabytes per second, in both cases, you can decompress at about 1 gigabyte a second. And then the other one we were going to talk about was the redacted replication. So this allows you to replicate data with specific exclusions. So basically what you do is you start with a data set that has a mix of regular and secret data in it. You make a snapshot and clone that. And in the clone, you overwrite the sensitive data. So you can zero out all the credit card numbers and the social security numbers or the passwords or whatever. So that allows you to back up a database and blank out that important information. Then you use that clone or the blocks that change that clone as a mask to mark which data is sensitive. Then you can create a ZFS bookmark to keep track of that and do replication, including later incremental replication, to copy that data set off to a remote backup or into a dev environment while excluding that specific subdata. So I'm going to pause here for a second to answer some of the questions that have come in. So if you have any questions, do submit those. And if you want to get more advice, remember that you can reach out to us at Klara, and we provide FreeBSD and ZFS advice. That's our business. So Dennis asks, is it possible to change the compression type of an existing file system? So the answer is yes. You can just do ZFS set compress equals Zstandard -5, but this will only affect blocks written after you change it. So any data that's already on disk that was compressed will be compressed with the old setting, whether that's off or LZ4 or gzip. But any blocks that you write that are new will now be compressed with the new compression algorithm. So that also means if you modify a file, any of the parts of the file that change will be rewritten with the new compression. So in those indirect blocks that we showed when talking about the resilver, it contains a bunch of information about the data, including the checksum, but also what compression algorithm was used for it, what checksum algorithm was used for it, how big the original version and the compressed version are. And so because of that, you can actually have one file that's made up of 10 blocks where every one of the 10 blocks is compressed with a different compression algorithm, and ZFS will just deal with it. So you can change the compression type of an existing file system, but it'll only impact newly written data. But if you want to rewrite it, you can take a snapshot of it and use ZFS replication and basically rewrite all the data and tell it to use the new compression algorithm. And so existing data could be compressed more by upgrading to a better compression algorithm that way. Are there any other questions so far? Okay, I'm going to move on, but if you have more questions, do submit them and we will get to them at the end. So now we can talk a bit about upgrading any existing installations. So you already have ZFS running somewhere, but you're using an older version of FreeBSD or Linux or something else, and you want to get up to OpenZFS 2.0. So many of the minor improvements are available simply by upgrading the version of ZFS. So if you're on Linux, that could just be installing the new RPM or APK or whatever, or as we'll talk about in the next slide, installing the package on FreeBSD. And once you have the OpenZFS 2.0 tools and kernel module, you will have access to a lot of the minor improvements. However, for the major features, like the sequential scrub or the Zstandard compression, and so on that we just talked about, those require changes to the format of the file system. And so you have to use zpool upgrade to upgrade your pool to support those features, and then you can use them. The downside to this is that once you upgrade a pool, you can't undo that. And once it's upgraded, the pool can't be imported by an older version of ZFS. So if you just want to try it out, you can install OpenZFS 2.0 and play with it. As long as you don't do zpool upgrade, you'll still be able to import it on the older version that you started with. But once you zpool upgrade, you can't go back from that. Well, yeah, you can't go back from that. But if you do, one best practice that you might want to consider is before doing a zpool upgrade, you can create what's called a checkpoint. So a zpool checkpoint is kind of like a snapshot, but it's for the entire pool. So it actually keeps the Uber block from the time of that checkpoint in a special location and disables all overwriting or freeing. So while the checkpoint exists, no data will ever be, no sector on the disk will ever be reused, and no space is ever freed. But this allows you to make some changes and then decide you don't want them and do a whole pool rollback to the point when you created the checkpoint. So it's always a best practice to create a checkpoint before you do a zpool upgrade. In case something doesn't work out, you can roll back. But remember, when you revert to a checkpoint, everything you changed is undone. So any files you changed, any data sets you created or renamed, any disks you added, anything you changed can be undone that way. But once a zpool upgrade is done, you can't unupgrade it so that you can port it on an older system. Another interesting thing about these features is that in ZFS, features are a tri-state. So, for example, the Zstandard compression feature, it has 3 states. Disabled, meaning you're not allowed to use it because you haven't done the zpool upgrade yet. Enabled means it's able to be used, but is not currently being used. If a feature is in the enabled state, most times that means that it can be imported on an older pool or an older version of OpenZFS because you're not using the feature, so the older version doesn't need to understand that feature. But as soon as you set, compress equals Zstandard on a data set, it will switch that feature to be active, meaning it's in use. And it will stay in that active state until you delete every data set that ever used Zstandard. So once you've deleted the last data set that was using Zstandard, the feature will go back from active to enabled. However, OpenZFS 2.0 includes some other features, including, I think, the bookmark v2 and a couple other things that get activated automatically, like the space map v2 and so on. So once you zpool upgrade, the pool is not compatible, but some individual features are designed to not make the pool incompatible unless you're actually using them. So now talking about some of the impact on existing installations. So if you have kind of related to the question we just talked about with the, what happens if I switch compression algorithms on existing data? What happens if you start using some of these new features on existing pools? For example, a little bit before OpenZFS 2.0, there was a new feature added called metadata allocation classes. This allows you to add a VDEV and specify that this VDEV is only for metadata or only for dedupe or something. So with this feature, if you just add a new metadata VDEV to your pool, obviously that's not going to rewrite any of the existing metadata. So it means that as you write new data to the pool, the metadata will be stored on that special VDEV, but any existing data its metadata will stay where it was. But over time, as you modify existing data or write new data, that metadata feature will kick in. The same like if you start switch your compression to Zstandard, as you write new data or modify existing data, it will get compressed with the new algorithm. And eventually, some portion of your data will be all written the new way. Depending on your use case, you might almost overwrite all the data on your system frequently, or you might have some data that doesn't get modified for 10 years and so never has a chance to be recompressed. One of these features that doesn't quite work that way is ZFS's native encryption. The encryption parameter must be set on a data set when it's created, and all blocks written to that data set are encrypted with that master key. You can change the user key that wraps that master key, but you can't just turn encryption on or off. You have to set it when you create the data set, and then all data written to that data set has that encryption. So if you're interested in using this new OpenZFS 2.0, but you're still on FreeBSD 12, FreeBSD 13 will include OpenZFS 2.0 or maybe even 2.1, depending on the timing. But FreeBSD 13 won't come out until March of 2021. So we got a couple of weeks left. So if you want to start playing with this now and you're on FreeBSD 12, you will have an older version of ZFS built into the operating system, but you can install the new OpenZFS 2.0. So if you're on 12.1 or 12.2, you can install OpenZFS from the ports or packages system. It's called sysutil/OpenZFS, and OpenZFS-kmod. There's 2 parts. So the OpenZFS package will have the updated ZFS and zpool commands and all the other bits, and the kmod has the kernel module. So the main thing you have to do is in your loader.conf that controls what kernel modules get loaded at boot. Instead of loading the built-in ZFS.ko, you load OpenZFS. And so this will load the new kernel module and give you access to the new features. The other thing is, because of the way packages work, the ZFS and zpool commands will still, for the old version of ZFS, will still be there in /sbin. And the new versions will be installed to user local sbin. They are compatible, but the old version of the tools doesn't understand the new features. So in order to, for example, enable Zstandard compression, you have to use the ZFS command from user local sbin. So you might need to change your path environment variable to look in that place for the ZFS command first, instead of /sbin, which is normally searched first, so that you find the right version of the ZFS command so that you can use the new features. The other thing to watch out for is obviously when you're upgrading your kernel to a newer version. For example, when 12.3 comes out, you'll want to update and rebuild the OpenZFS.ko for 12.3 and have that installed in /boot before you reboot onto the new kernel. Otherwise, it won't be able to load the kernel module, and then you won't have ZFS support. And if that's your root file system, that could cause you some problems. But in general, it's fairly straightforward. The instructions are in the package message when you install the package, and this allows you to have access to the new OpenZFS 2.0 features on the existing versions of FreeBSD that don't have it yet. So how does OpenZFS 2.0 impact your planning for new installations? I think the biggest change is that with this new sequential resilver, you might more strongly consider using mirrors instead of RAID Z. For a lot of workloads, especially things like hosting VMs that you're then using ZFS as the backing store for a hypervisor, whether that's VMware or KVM or Zen or whatever. The best practice has been to use mirrors for quite a while, because mirrors provide more IOPS, more separate operations per second. But with the new faster resilver, they also have that other advantage now. So while the storage efficiency isn't as good, the performance wins are really large and mean that you might even more strongly consider using mirrors instead of RAID Z in order to get access to the sequential resilver feature. While not specific to OpenZFS 2.0, a relatively recent feature is device removal. Again, in the case of mirrors, but not RAID Z, you can remove an entire VDEV, so a pair of mirrors, from a pool and actually shrink that pool. So I've never personally had the problem of needing less space than I had, always need more, but depending on your use case, you might actually need the ability to shrink a pool, and again, using mirrors gives you that option, whereas RAID Z does not. And we talked about the allocation classes feature, being able to separate metadata or small blocks onto a faster device can improve things. And again, if you do that from the beginning, then that means all the metadata will be there. But remember, those allocation classes, if they're going to have all your metadata, they need to be redundant. So you might want to make that a 2- or 3-way mirror to make sure if you lose all the metadata, then all the other data is gone. But one of the big advantages of doing that with allocation classes is the ability to reduce fragmentation. Metadata are these smaller blocks, and having them mixed in with the bigger blocks can mean things don't line up as nice. Whereas if you can take all the small blocks and put them over here and just have your other disks have all the big blocks, you'll have less fragmentation that way. Another big one to consider is ZFS encryption. Unlike regular whole disk encryption, where once you've entered the passphrase, the whole disk is available, with ZFS encryption, you can have different keys for different data sets. So if you have some data that doesn't need to be online all the time, you can actually unload the key, and then that data is back to being encrypted and not readable until someone loads the key again. So if you have some sensitive data that you say only need for billing, so you only need to load it once a month, you can have it unloaded and actually at rest encrypted all the times that you're not using it. And as we talked about, Zstandard compression can greatly improve your compression ratios, and that might be of quite a bit of interest. Okay, let's see what else we have for questions now. So Dan asks about TrueNAS Core, which is based on FreeBSD, which uses OpenZFS 2.0 and is based on FreeBSD 12.2. Yes, that doesn't require any additional configuration. IX Systems has already done the work there. They basically compile FreeBSD without ZFS and then add the ZFS port in after. But that's an appliance rather than doing it yourself, but that is also an option. So yes, TrueNAS Core does have OpenZFS 2.0 as well. So Reynes asks, is it possible to install OpenZFS 2.0 on FreeBSD 12.2 if you're using ZFS on root, whether it's EFI or legacy BIOS? And the answer is yes. You might need the newer bootloader. I'll have to double check that one for you. But yes, but you might need to get the newer EFI bootloader code from FreeBSD 13. But I'm pretty sure 12.2 included everything that you needed for it. I admit most of my OpenZFS 2.0 systems are FreeBSD 13, and so I didn't have to worry about it. But yes, you can use OpenZFS 2.0 as the root file system. And then Danny McGrath asks, are there any plans to allow you to change settings such as the compression or copies equals, and then have a resilver or some kind of background update of the file system? Most of that falls under the umbrella of a feature called block pointer rewrite, which would basically go through your data and be able to update it in place. There are not currently any plans for that. There's concern that the level of complexity required to do that would mean it would be very difficult to then add any future features to ZFS. So, Matt Ahrens has said, if block pointer rewrite were to happen, it would probably be the last feature of ZFS because it would complicate everything so much that it would be hard to add additional stuff. So currently there are no plans for the ability to update data in place, but somebody might have a bright idea one day and make it possible, but currently it is not. Some other features like the device removal that we talked about were done, originally were thought to need that block pointer rewrite, but they found a way around it and built this feature to avoid having to create block pointer rewrite. So it's not impossible, but not currently, there's not currently anybody working on it that I know of. So Erwin asks, he says, I understand on Linux, ZFS native encryption is slower than Lux dmcrypt. Is this true? I'm not sure how they compare directly. And he asks if there will be performance improvements in OpenZFS 2.0. I think there were some performance improvements to use more of the AES-NI and other offloads to improve performance. It can also depend which algorithm you use, but the AES GCM should be faster, but the default, I think in ZFS on Linux 0.8 was AES CCM. So I would suggest trying AES GCM on OpenZFS 2.0 and seeing if that is faster. So an anonymous attendee says that the lack of the block pointer rewrite feature explains why encryption can't be applied to existing data sets. Yeah, it's because to encrypt an existing data set, you'd have to go back and rewrite all the data. So you can do that outside of ZFS, kind of by snapshot the data set, ZFS send it to a new data set that has encryption enabled, then all the data will be read and written again and encrypted, and then you can delete the old copy. But ZFS doesn't support doing that in place, without needing to double the space temporarily. So Simeo asks, is it possible to use BEADM, which is a boot environment management tool, and a ZFS encrypted pool? As I know, it's currently not possible. So the bootloader itself does not support encryption. But so if your operating system, the root file system, is not encrypted, but say your home directory is, the FreeBSD bootloader can still boot that. But if the root file system is encrypted, then it can't. So as long as none of the files required during boot are encrypted, then it is possible to use ZFS encryption and boot environments. You just need a new enough bootloader that knows that it can ignore the feature flag that says that encryption is in use and just try to read the root file system. As long as it's not encrypted, it'll work. So Libormir asks about adding encryption to a data set. I think I just answered that, but the best way is basically to either use ZFS replication or just copy your files to a new data set where you've enabled encryption first. So basically, you just have to copy the files to an encrypted data set, either manually, or you can use ZFS replication, ZFS send, to rewrite all the data. The only downside is it requires temporarily that you have twice as much space, right? You're going to need the plain copy and the encrypted copy. And then once you've copied it all, you can get rid of the plain copy. The downside to that, obviously, is that the disk in the slack space might still contain a lot of that unencrypted data. So you'd have to do something like the zpool initialize after to go through and overwrite all the free space with zeros. So Dennis asks if there's any benchmark data available on the different compression types. There is some. I posted some benchmarks I did on the OpenZFS developer mailing list when I did it. Also, in the original pull requests, there are some graphs. But the benchmarks really highly depend on what type of data you're writing. So whether it's device removal or, whether it's a database or regular files or media or whatever, the type of data and the record size have the biggest impact on performance. So some general benchmarks are informative, but to really see what one's best, you kind of have to run your own benchmark on what your data is. But I did a bunch of benchmarks using the FreeBSD source code as text data that's compressible, the Postgres database, and a couple of VM images as different exemplars. Jess asks, does VDEV removal incur any performance penalty? Yes, but the penalty is reduced over time. So the way device removal works is it finds large blocks of data on the device that's going to be removed and rewrites them somewhere else. And basically, it keeps this indirection table. It just says, the first gigabyte of data that was on the device removed is now on this other device. And it builds this table of all of the blocks that were on, ranges of blocks that were on the device that you're removing, and keeps that in memory. And so after you do a device removal, when you do zpool status, it'll tell you how much memory is being used by that indirection table. Over time, when you overwrite a block that was on the disk that was removed, it gets written normally and can be removed from that list. So over time, the performance penalty will keep going down, but the penalty is mostly just that table in memory, so that every time you try to read from the disk that's not there anymore, you can go tell it where that data actually lives now. So it's not a large penalty, and it's reduced over time as the data is updated. Anonymous asks, would you recommend using ZFS for the boot disk on an EC2 instance? Yes. Having access to boot environments, this thing where you can snapshot your root file system, say before an upgrade, means that you can use the features of the BECTL tool on FreeBSD to say, all right, I've upgraded from 12.1 to 12.2. I snapshotted the system before I upgraded. What I want to do is boot the next time only into 12.2. If it doesn't work, then you can go into the EC2 console, power cycle, and it'll revert back to 12.1 and let you get into the machine and try to fix it. Whereas, because EC2 doesn't really provide a rescue console, if you break the machine during an upgrade, it could really be annoying to fix. Plus, you get access to things like transparent compression and encryption and all the rest. So the features of ZFS make it really, really interesting. So I do recommend it for EC2. And then we're almost out of time, but Walter asks, will this webinar be available for review later? Yes, it's being recorded, and we will post the video on our website in the webinar section as we did with the previous ones. If you weren't aware, we've done 2 previous ZFS webinars already, and those are available for you to watch as well. Okay, we're out of time, but just remember that if you need help with ZFS, you should reach out to us, either via email on our website, or you can use Twitter or LinkedIn, whatever you prefer, but check it out. Also, if you go to our website under the articles section, we have a lot of written material about ZFS. For example, if you are not that familiar with the L2 arc that we talked about, we have a whole article explaining how that works and showing some benchmarks and so on. So you might be interested in that. And of course, as we said, we do support for FreeBSD and ZFS. So if you need that, reach out to us. So thank you for coming, and we'll see you next time.